With that having been said, please allow me to introduce Joseph. And Joseph, I'm not even going to try for your last name. I do apologize. And Joseph's going to talk to us about scaling from 0 to 20 million users. Joseph, take it away.
Thank you, Kyle. Okay, so hi, everyone. My name is Josip. I'm the CTO at a company called SofaScore. We have an app that delivers live sports results and statistics to more than 20 million users worldwide. And we do everything in-house. So from idea generation to design, development, and infrastructure. And this is a story of how we got from 1 user to more than 20 million, and what we encountered along the way, where we failed, and how we solved the challenges that working on this scale presents. So a little bit about the current system and the usage. So currently the system handles around 20 million monthly active users, and those users generate more than 180 billion requests each month and deliver more than 600 terabytes of data to our end users. As for the tech stack, so we use a lot of different technologies. Backend is written in PHP 8.1, and we are using the Syfmony as a framework. And for the database, we utilize Postgres. Other than that, we have a couple of services written in Go and a whole lot of other technologies for our front-end applications. We differentiate ourselves with speed and quality and have a really high user satisfaction, which can be seen on Google and App Stores. So we kind of take great pride in this and try to have the fastest possible application that we can have. And our growth has been organic, so without any external investments, but the number of users rose rapidly over the years. And that means that we actually had quite some interesting problems to solve along the way. But let's go back to the beginning. So in the beginning, we only had 1 server, and that server was actually a shared server among multiple projects at the same time. And since it was shared among multiple projects, it had VHM and cPanel on it. I'm sure that some of you remember that period of time. It had Apache PHP 5.3 installed on it, MySQL database, and this was in 2010. So the limits on that server were hit soon enough, and we had to buy a dedicated machine. So we just replicated the setup we had before. We actually weren't managing the server. At that time, we had a hosting company that did it for us. So they just did everything the same. And at the time, the app itself, the backend, was written in Kohana. Maybe some of you heard it. It's actually a fork of CodeIgniter. Both frameworks are dead. But at the time, that's what we were using. So when we got a little more popular, 1,000 users would come at the same time on the application, it would crash. The server would give up. We couldn't handle that kind of load. In other words, not good. So everything was also on the same server. So it was kind of difficult to figure out what was using the resources and how we can optimize the app better. This is what our office looked like. So just 2 guys working on a couple of big old monitors, and you can notice the grain image of ancient times. But back to the server issues. So we got a suggestion from our hosting provider to put Nginx in front of Apache and PHP. And they said that this should improve the resource usage because Nginx was actually better at serving static content than PHP is. It did help, but not by a lot. So we kind of kept searching on what we could do next. And of course, the next logical thing is just instead of 1, you have 2 servers. So we split it to 2 halves. We had a PHP application on 1 server and a database on another one. This was, of course, better because you have more computing power. But it also meant that we can see where the bottleneck is. Also, the PHP doesn't really use a lot of memory. So we had some RAM lying around. So we installed memcached to cache the database queries in memory. And this actually had the effect of significantly improving the response times. We also implemented the full page cache, and this also improved response times because templating didn't have to get calls, it could be the content could be immediately pulled from the memory. And this worked great when the load was increased, but the site broke down again during peak times. And that's due to the cache stampede effect. So that's what happens when cache expires, and now all of the users try to access the same content at the same time. Since there was nothing in the cache, every single request will have to render the full page cache, the full page, before actually saving it to the cache. And the longer it takes for the page to render, the bigger the effect is on the whole system, because all of the other requests also have to get calculated and then saved to the cache. And this leads to spikes, and pretty soon your database and your whole server will die. Everything will break down. So the important part of trying to optimize your system is to kind of be aware of how your users will use the application. And we had a really good understanding of that. We could predict when the next big spike is going to be, and what pages will be requested. And we also knew the number of followers for each match, so we knew what pages will be the most popular. And people also usually look at the matches that are live right now or have been recently. So what we want to get to is this, to only have one request going through the cache and not all of them. This is called request coalescing. And to do this, we actually use the knowledge that we have of our own system and kind of calculated what is going to be happening around this time, that's the matches that are happening right now, and pre-saved those caches in the cache itself. We did it by saving everything to memcache via the worker. So the worker would just look to see which matches were the most popular. It would proactively fill the cache, save the full page cache to memcache, and then everything would work out of the box. The most popular matches would always be available to the end users, and they wouldn't have to wait. But still, PHP is slow. The framework had to be bootstrapped, the controller had to be instantiated, the cache had to be looked up, and this all takes time and resources. So the way peaks work for us is 15 minutes before the game starts, a lot of users will come online. And at the start of the game, that number will double. And then it will slowly rise during the time the game lasts. So 15 minutes before a really big match, we could already tell from experience if the server is going to have issues. And then El Clásico happened. So for those of you that don't follow sports, this is when the two of the most popular soccer teams play against one another, which is Barcelona and Real Madrid. So it's a global event, and a ridiculous amount of people want to follow this match and want to watch it. And 15 minutes before this game was about to start, we noticed that the server was really slow and had no solution for it. And we only had 50 minutes to try to figure out what can we do to kind of prevent the server from dying. And you might wonder, what can you do in 15 minutes to kind of solve the issue and to keep the server alive? One of the ways is just to hope that enough people will give up and that the rest will be able to see, but that's not really a good solution. So it occurred to us that PHP is slow. It's really slow compared to Nginx. And Nginx is really fast in serving static content. So what we did is we opened the page while we still could, while the server was still working. And we had an idea to just do file save as and to save the match, the HTML content in a file. We then uploaded that file to the server and wrote a rule for Apache that would say, if El Clásico is requested, then return this static file from the disk. And this was just in time before the server was about to give up. And did it help? Yes, it did. The load on the server dropped. But now the El Clasico page, of course, since it was starting, it wasn't live. So we actually ended up watching the match on the live stream, and every time something happened, we would change the HTML by hand and upload it to the server via the FTP. I know that probably most of you are now laughing at how we solved this problem, but it did work. It was a great success. At that time, we knew we had to get more servers because 2 wasn't enough. And this was 2012. Fortunately, the website itself was written to be stateless from the beginning. So it shouldn't be that hard to put it on multiple servers. And given the nature of the application and the need to automatically handle an extreme increase in user activity during peak times, we kind of decided that it was best to move to the cloud and to make use of the auto-scaling. So in May 2012, we moved our infrastructure to the cloud. And of course, there wasn't really a lot of options at the time, so we've settled for AWS. In that move, we've replaced the Apache with Nginx and PHP FTM and just didn't install anything else from the like VHM or cPanel, and we left our hosting company and decided to do everything ourselves. The most important thing that we did in that time is that we started using Varnish, which is an HTTP reverse proxy that can cache the content. This has dramatically improved our performance. So Varnish sits in front of Nginx and PHP and caches everything that is cacheable. So the PHP framework actually doesn't need to be bootstrapped, and the cache is returned to the user by Varnish. And that whole process of looking up the cache and returning everything from cache just takes a couple of nanoseconds. So it's extremely fast. And we also had no need to pre-populate the cache to avoid the cache stampede, because Varnish has a built-in request coalescing. So what it does is, if it gets a number of the same requests for the same endpoint, it will actually put everything on hold and just forward one. And then when it gets the response, it will return the same response to all of the clients waiting. So that has enabled us to actually remove the memcache as well. We also changed the deploy. We were no longer using FTP to deploy new code. We started building AWS images by checking out the code and creating a new AMI with all of the caches warmed up. And since it was trivial to create new machines, we also split the workload. There were multiple instances for the web app and a separate machine for workers and cron jobs. So auto-scaling was set up based on the average CPU usage, and that worked great. Like when demand increased, we got a number of new machines automatically, and also if we needed a larger database, we could just increase the type of the machine. And also, just for simplicity's sake, Varnish was baked into the image together with Nginx and PHP, so it was trivial to scale as well. And in August 2012, we had a peak, which was around 3,000 users at the same time, according to Google, and everything worked. We also were in a process of switching to a new data provider for our scores, and we decided to ditch Kohana because it was dying, and decided to move to a different framework. And we chose Syfmony because it had a really vibrant community and a stable code base. So that's what we did. We started rewriting the application to Syfmony. And also, this was 2013, mongoDB was all the rage. And we were having some issues with our MySQL database. And since we were rewriting everything to Syfmony anyway, we thought it would be a great idea to put all of the sports data, analytical data, to a NoSQL database because, you know, web scale. And MongoDB actually worked well for some time. We also, since we switched the providers, we needed a way to accept a file from the provider and parse it asynchronously. So what we did, we implemented a queue. A new job is created, saved to the disk, and a job is dispatched. That way we can have a surge of data without actually affecting our server and the server being overloaded in the process. And the first queue we were using is actually Gearman, which was quite popular at the time. Probably some of you recognize the name, but we had some issues with it because the memory usage wasn't really what enables us to scale to more jobs. So we switched to Rescue, which is based on Redis. This worked well for some time, but also issues. And then we switched to Beanstalk, which is what we use now. We have more than 120 different services that asynchronously process jobs, and it works flawlessly. So really, really good piece of software. And MongoDB worked great until it was causing more problems than it solved. I'm not going to go into all of the problems that we had, but we did have enough. So from strange issues with duplicate keys during replication to developer errors with data types because short and long integers do not compare with the quality operator. Data was extremely difficult to analyze, and we missed the times when we could just do a simple SQL table join and make sense of the data. MongoDB would also lock an entire collection at that time on writes, and we had a lot of writes, which was also a problem. And it also didn't help that there was no support for foreign keys, so data consistency became an issue. So we had decided that the move to MongoDB actually was a bad one, and we wanted to switch to a relational database. After searching around, we've settled on Postgres. Why Postgres? Well, because it was open source, and after doing some benchmarks, we saw that we could get an amazing read and write performance. It had advanced SQL capabilities, which do come in handy, since we want to analyze historical data and give insights to our users. And the biggest one of all, it had almost no locking, meaning that you can read and write at the same time and do so consistently without locking the table. This mechanism is called multi-version concurrency controller, MVCC, and it works wonders. To give an example of that performance that we get from Postgres, this is our current machine can handle around 1 million queries per second and around 90,000 transactions per second. One transaction is actually 5 data changing operations. So insert, delete, and 3 updates. So after we were happy with the performance of the database, we started calculating how long it would take us to rewrite the entire code base. The problem was we didn't want to be offline for 1 second while we were doing the migration because the number of users rose and they would be complaining. So it was something like this. So replacing important parts of the car while the car was driving on a highway, doing 100 miles an hour. But we decided that it was worth it. Fortunately, since we were using Doctrine ODM, it was not as horrible as you might think. So we wanted to switch from the Doctrine object document mapper to the relational mapper. So what we ended up doing was to timestamp all of the collections in MongoDB with a modification date. And we wrote a script that would look for changed entities and transfer them to the new relational database. It took us just a week to write this tool, even though the code base was quite big. Then we ran it in a loop to transfer all of the changes all the time. And then we deployed a new machine with the new code, the new relational code, to see how it performed on a separate machine. And we left it for about a week and kept checking for inconsistencies between MongoDB and Postgres. And when we were sure that everything was fine, we just deployed everything and everything worked, which was surprising. Nowadays, I would be much more careful on how we would do that. So the pros and cons. We lost the simplicity of MongoDB configuration together with leader election and replication. But we did gain stability and analytical power of our relational database. So we would no longer have to worry about data consistency on a database level. This setup was quite robust. Developers had more power with the new database. They could easily aggregate data. The auto-scaling did its work of spinning up new machines when needed and then removing them when nobody was online. So most of it was on autopilot. This is how we looked at the games. And you can notice in the lower right part of the screen, almost 5,000 users at the same time, everything is working. And a month later, that peak was almost 17,000 people at the same time using the site. So the peaks were increasing at an almost exponential rate, which meant more problems for us. And of course, the more features you have, the more endpoints you have to have. And also more endpoints mean that your hit rate for the cache is lower. If you have more users, you also have them accessing different endpoints. And that all means that more servers will scale up. If you're on the cloud, that shouldn't matter, except for the money, of course. But for our setup, for simplicity, every machine had its own varnish that would cache the request for a particular backend. So no request had to be recalculated twice if there was just one machine. But when you get more users, you get more machines, and more machines mean that every machine will have its own cache. That means that the number of requests going to the database will scale with the number of machines you have, which is not as efficient as it could be. And also, if you have 10 machines, every one of those would go to the database, and it would scale linearly. Since the cache isn't scaled, isn't shared, everything goes to the database, and with enough machines, it really doesn't scale. So it's not that difficult to solve this. What we did was we extracted varnishes to two separate machines that then had the same backends which had the ability to be auto-scaled. And that meant that during the times when backends were scaled up to 10 machines, the cache wouldn't degrade. The hit rate would remain the same. So every request in this particular case was executed at most 2 times because there are 2 varnishes. Each of them has its own cache, regardless of the number of the backend servers. That's great, but still, it's not optimal. So you always get 2 requests. 2 requests aren't bad, but if it was just 1 request, it would be even better. So we were looking at how to solve this, and we implemented a 2-layer varnish architecture, which has multiple varnishes in the first layer, and then they all point to the same varnish on the second layer, and then that varnish goes to the backend servers. So with this, you actually get a global request coalescing, and it works great. Of course, you'll probably notice that this is a single point of failure. So if this varnish fails, everything is offline. There is no redundancy, and you can get away with this for quite some time, probably, if you have stable machines. But if you want to sleep at night, and we definitely do, this is something that needs to change. So the way to solve this is by sharding based on the URL of the request. A specific URL will always follow the same route every time, regardless on what machine handles the current user. And thereby, it will always hit the cache while also providing redundancy. So different URLs will go on a different machine. And this means that you can also scale both layers independently and have request coalescing on a global scale. And if any one of the varnishes fails, the others will simply take over because there is a health check for machines built into the varnish. And we could now cache everything. And with that setup, we also saw an opportunity. So we have a read-heavy application, which is perfect for caching. So we carefully designed the API to be as cacheable as it can be. So that means no query variables. Everything is REST compliant. The content was split into multiple endpoints, so they could be cached and invalidated separately. And the cache for the most commonly requested API calls was increased. And we also put in place cache invalidation. Our hit rate during peak times was over 99%. So more than 99% of requests was going out of the cache, and 80% during the rest of the day. And cache invalidation is really, really tricky thing to do. So that's one of the hardest things to do in computer science. And for this, we developed our own in-house library. It's for Syfmony. It's called Purgatory. And that enables us to purge the content from the cache with ease. So the only thing you have to do is to write an annotation or an attribute and tell the library on what entity your endpoint relies on. And then it will auto-generate the entire URL for you when something changes. And it will fill in all of the placeholders that need to be filled in. And it will purge the content. It will just purge that URL without anything else. So it will preserve your cache. It has a lot of advanced features, transversing the relational graph, purging only on the parts of the entity and stuff like that. It's open source, you can check it out. I can do an entire talk just on this, but there is no time, so I just urge you to check it on GitHub if you want. This is the annotation that needs to be written. And the installation is as simple as Composer require, and there is a simple config to enable it. Okay, so now the cloud was great. It was extremely flexible. We could do a lot of things simply. There were a lot of managed services that we could use. And with this setup, we had 54,000 real-time users with ease. But it all came with a price. We use a lot of bandwidth, and bandwidth is expensive, especially in the cloud. So we were spending more money on bandwidth than on the rest of the infrastructure. And it wasn't actually going to stop. So the price of our data transfer was only going to increase with the number of users. And we won't actually need that much more machines. We don't need the scaling because everything is just being delivered from the cache. We've looked at a lot of different CDNs, but they were expensive too. So we kind of started to look for an intermediate solution. And since most of the bandwidth is actually cached and the content is served from the varnish is not something that we needed to scale. So we came to an idea to buy a couple of machines in data centers where bandwidth is much cheaper to serve the content, but keep everything else in the cloud. So the brain of the application is still in the cloud. And this worked extremely great because we still had the auto-scaling capabilities and all of the goodness of the cloud, but we cut the cost of the caching layer and bandwidth by 10x using this approach. And we had a pretty good understanding of our infrastructure needs. So we were at a point where we no longer needed the auto-scaling as much as we did in the early days. Because the peaks didn't have such an impact because of the cache. So we did the math on the amount of money we were spending on AWS and what kind of machines we could buy in a data center for that money. So we came to a conclusion that we would use less money if we over-provision the system to handle the biggest load, the biggest peak that we could ever have for less money. So we decided to move everything back from cloud to data center. And it wasn't actually that hard since we weren't relying on AWS services that much. So we first went with a test, of course. Database replica was set up in a data center. App servers were set up to read from that data center replica and to write everything to a master instance that was on AWS. And we had everything running in both data center and AWS, and it worked. And when we were satisfied with how everything was set up, we just moved the master database itself, and that was just a simple failover to do it. And to replace the AWS stuff, so images were replaced with Docker. EC2 was replaced with Docker container. We used Cloudflare as a load balancer, and it also has an added benefit of a DDoS protection and local cache, and this improves latency. And we already had a cache invalidation system, so it was really easy to also invalidate it on Cloudflare. And this has resulted in a significant price reduction for us. In 2016, we've passed 100,000 real-time users using this system, no issues whatsoever. And we also moved from manual Docker deployment to Docker Swarm, which is a container orchestration system to simplify the deployment and management of different services, and also to increase the availability of our infrastructure. And we have a really specific way our users interact with the app. So this is a graph of requests in time. So everything is real time, everything needs to be fast, and we want to deliver the score change to the end user as soon as possible. And when they receive the notification, they pick up their phone and open the app immediately. So this means that we have a real surge of users all going online at almost the same time, and then that can put quite a strain on the infrastructure. So the pattern is so unusual that we've caused anti-DDoS mitigation to trigger on such events. And Cloudflare actually had to put a special exemption for us for some of their rules so that they are not activated for our account when something like this happens. It took us quite some time to convince them that it's an issue on their end and not with us. We actually had to go to their US office and speak with them, with their engineers in person. And we also had the same issue with our data provider. So a lot of users come online at the same time. This is September 2017, so 230,000 real-time users. And next year, 310,000 users. And soon after that, it was 423,000 users at the same time. To optimize the app itself, so we are using New Relic, application performance monitoring, and we regularly look at what's most time consuming. So there's an option in New Relic that's called most time consuming, and it's extremely useful for pinpointing the ideal endpoints for optimizations. You don't have to use New Relic. There are really a lot of good APMs out there. So this is a real-world example of a problematic endpoint that we've detected. And the impact of a few optimization is really staggering. So in this case, the response time dropped from 200 milliseconds to 50 milliseconds. And this is just by having New Relic and kind of seeing where we can optimize. But sometimes you cannot optimize any more than it's already optimized. Maybe the endpoint is the fastest that it can be. So what can you do then? So if there is nothing to optimize, we can simply increase the cache on an endpoint. And this is really simple thanks to Purgatory, so the cache and validation library I've mentioned. There is an exponential drop in requests hitting the backend just by increasing the cache just a little bit. So it makes a really big difference. And I often get the question, so what if the number of users exceeds the current capacity? Like you're not using the cloud, how will you scale? Won't you have an issue? And the answer is no. So we've implemented a hybrid cloud approach. Our data center also offers a VPS servers, and they can be controlled via the API. So something similar to AWS. And since we're using the Docker Swarm, scaling is really easy to implement. So when request latency increases above a certain threshold, an alert will be triggered, which will then spin up VPS instances that will automatically join the swarm. They will pull the latest image, join the cluster, and the system will scale. If after a certain cooldown period, the latency is still high, new instances will be spun up and the system will scale. Just to clarify, I'm not saying that you should abandon the cloud, but there are times, like in our case, where that can have a massive difference in terms of pricing. You, of course, have to be prepared to do some of the things yourself, and you have to compare the cost savings versus how many engineers you will have to kind of cover that increase in work. But up until a year ago, we only had one engineer working on the DevOps part of our system, and it was only part-time, so it's doable. September 2019, 600,000 real-time users. And that's when we figured out that real-time isn't actually real-time. It's in the span of 30 minutes, but it's the same number. So we could kind of track our progress. That means 600,000 users in a span of 30 minutes. 2 months after that, 800,000. And we got to thinking. So all of our servers are in a data center in France, which means that our users in Europe get a great app experience with very low latency, and the app feels snappy. But we always wondered how the users outside of Europe perceive the app, because physics and there's latency happening with the speed of light. So I sent an email to one of our chat moderators that's based in New Zealand to ask him if he would be willing to record the video of the app so I can see how the user experience is in Australia. To which he replied with the video of the app and said that everything is fine, everything is fast. But when I was looking at the video, I've noticed that while he was clicking through the app, there were loaders. They didn't last long, so it was like half a second of loading. But I honestly didn't know that we had loaders in the app. So that's how fast it is in Europe. But users in Australia didn't seem to mind because everything is slower for them. People usually don't bother setting up local data centers in Australia. So we had similar conversations with our users in Brazil and India, and we saw a great opportunity here. So we wanted to be better than the competition and try to provide an excellent user experience worldwide, not just in Europe. And since our caching layer is separate from our infrastructure, we can just simply put it on machines all over the world. So we did just that. We bought a couple of machines in different parts of the world. And Cloudflare has the ability to route traffic to the nearest, to the server nearest to the user. And all of those servers would then connect to the France. And this had a dramatic impact on the average latency in those places. So for example, in Australia, the latency dropped from 350 milliseconds to below 50. So you might ask yourself, shouldn't a CDN like Cloudflare do this? So that we don't have to, and yes, they do. But they have a lot of users with a lot of content, and not all of it can be cached. So we've observed a 2x improvement by setting up Cloudflare in terms of latency, but a 10x improvement with our own system. So you do get a benefit from CDN, but by deploying our own cache servers, we can control the amount of local cache on each continent and ensure that there's always enough for our users. And by lowering the latency, you increase the user satisfaction, which then results in more organic traffic. December 2020, this happened. So we finally passed 1 million real-time users. And that's all on a system that works flawlessly, and it's all running on PHP. In 2021, something interesting happened. So a data center of the provider we're using burned down. Fortunately, it wasn't our data center, but it got us thinking that it's a good idea to have your application in multiple data centers, whether on-premise or in the cloud, because cloud is just somebody else's machine that can also burn down. So because of this, we switched from Docker Swarm to Kubernetes. And the most important reason for this is that it's data center aware, and that enables us to have database replicas in each data center, and PHP will just read from the one that's in the same data center as the application itself. We also have easy deployment. All of the machines are running the same code on all of the machines without any artifacts left over from the previous version. And PHP upgrades are really easy. We just bump the base image and deploy. If anything goes wrong, the rollback is simple. It's built into the Kubernetes. You just call the API and it will roll back everything for you. So we're really pleased with this, but it does add some complexity. October 2021, 1.5 million real-time users, so quite a jump from the last one. And PHP, it's great for API, but if you want to do real-time updates, it's not really that great. If you want to deliver data to the end users as fast as possible, the best way is to, of course, use a socket, like WebSocket or something similar. And while PHP can do this, it's not really what it was designed to do, especially not on scale. So for this, we're using Nats. It's basically a pub/sub server that's completely free and open source and can work in a cluster. It's really easy to deploy and use, and each server can handle hundreds of thousands of live connections on commodity hardware. And if you run it as a cluster, it will scale with no issues. It is great in combination with PHP. So we deliver all of the data via the API, and then just push out incremental changes via Nats to clients. So they receive the changes in just a couple of milliseconds. So the take home would be to be stateless where possible. It will enable you to scale more easily in the future when you need to add more machines. State is something you should be avoiding. Queue everything that is slow. I know that this is common knowledge, but it doesn't hurt to mention it again. Monitor everything, optimize something. You have to have good monitoring to be able to have a system that will scale, but you should try to avoid premature optimization because that's the root of all evil. Know how your users interact with the app. This is really important because then you can design the system to be as optimal as possible for that kind of usage. Cache, of course, this is something that's most important to us, and you can cache more than you know. So people usually say, oh yeah, but I have user personalization, I cannot cache it. Yes, you can. We also have user personalization. There are ways you can cache the content by grouping the users into clusters. And recognize the right tool for the job and change if necessary. So this is something that we did a couple of times. The most recent one in MongoDB, where we saw that it wasn't going to work for us and that we needed to change the tool and to make the switch. Don't be afraid to do that. And that's it. Thank you. I don't know, Cal, if you have any questions.
Wow, you nailed the time exactly. I mean, the entire talk was phenomenal, but the fact that you can bring it home and hit the moment is just great. Yeah, we got a question. Hang on. Let's see. Somebody asked, sounds like you've had multiple iterations where you would rebuild to match the increasing usage. Based on your experience, are there any telltale signs you get before you get the actual load problems that you might need to look at improving your setup?
Yeah, so it's definitely better to try to increase the capacity or rewrite something. And to do that, you have to have good monitoring. So the way we do this is we monitor everything. And when we see that something is increasing, we just proactively, we kind of extrapolate on how much time we have, and we start thinking about solution to possible problems. We even do it beforehand. So right now we have a system that works for this scale, and we already know which parts of the system might have issues in the future. For example, the easiest one is database. So when we hit the database limits, that's going to be a problem. The solution to that is to have a replica, but you also get to different problems with replicas. So we already have in our minds the next layout we're going to have in the database, and to denormalize some of the tables that will have the biggest usage in the future. But yeah, monitoring is definitely something you should have and kind of see the trend the system has and proactively plan for what you need to do. Yeah. You don't have to do it right away.
Great advice. Great advice. Tony will post the other. There's a couple more questions, but we're actually a little over time. But Tony will post the other questions in the Slack channel, and that way you can answer those, because I know people are very curious. This is phenomenal. You know, I keep saying I need to rewatch this because there's so much knowledge that I didn't get. This is the first one so far today that I'm going to say that I've got to make my team watch this one. And we're not nearly at this level yet, but I don't want to wait until we're in a need situation before people start understanding how to do this stuff. So thank you so much, Joseph. That was wonderful.